So in this video, we'll be solving a problem on connected system of bodies. And because this is a problem we are solving from kinematics point of view, we will also have to find the tensions in the strings, and of course the acceleration will be playing a very important role over here. Depending on what is asked and what data is given, we can apply different approaches on the same connected system of bodies. So in this particular video, we are following it. We are solving it from kinematics point of view. In other video, probably we'll cover the work energy or impulse momentum point of view as well. So because the tension and acceleration is very important to be found here, we will have to go with free body diagram kind of method. Let's start with an object, the free body diagram of an object, which is farthest from the force that we need to find. So here is our object. Let's put up all the forces on this. The force with which the body is being pulled, let's call it as tension T1. The weight of this object will be acting downwards, that is given as 500 newtons. There will be a normal reaction at the surface, and that let's call it as R3. And of course, because the motion is actually happening on the left side, the friction will act opposite to that motion, and that will be coefficient of friction is 0.2 times the normal reaction, that is R3. Now this is a problem on dynamics, so we'll also have to take an extra force, that is the force of inertia. And because the acceleration is acting towards left, inertia force will be acting towards right, the opposite to that is opposite to the acceleration. The value of this inertia force will be mass, that is 500 by g, times the acceleration with which it is moving. Now, having taken all the forces here along with the inertia force, we can apply the equations of equilibrium on this object. So let us start with applying the sigma v, summation of all the vertical components. R3 is acting upwards and the weight 500 is acting downwards. Total has to be equal to 0, and that gives us the value of R3 as 500 newtons. Next, let us go ahead and take up all the horizontal components. Fi is acting on the right side, tension T1 is acting on the left, and of course friction is acting on the right, so 0.2 times R3. So these three forces are acting in the horizontal direction. Let us substitute whatever values we know. Inertia force, I've just told you, that is 500 by g into A, minus tension T1 is not known, and of course see, the summation of all the horizontal components has to be 0, and here R3 value we just now found it as 500. Let us substitute. So that gives us the relation for T1 as 500 times A by G plus 0.2 times 500, that gives us 100. So this we will call it as our equation number 1. So let's take the free body diagram of the second object, that is W2 of 1000 newtons. Now it is inclined to the surface. Let's put up all the forces that are acting on this. The upward tension will be different from the tension that's acting at the bottom side. This tension will be of course equal to tension T1, because the pulley that we have here, that is weightless and frictionless, both sides of it tensions will be the same, but here the tension will be slightly different. So that is, let's take that as T2, and of course this is a pulley, frictionless, so on both sides of that pulley we will continue to have the same tension. So now let's come back to our free body diagram and put all the forces that are acting here. Weight of this will be acting vertically downwards, that's given as 1000 newtons. Tension T1 is acting on the downward side, tension T2 is actually pulling it upwards. There will be a normal reaction acting at the surface, let's call that as R2. And because the motion of this object, the acceleration is acting upwards, friction will try to oppose that motion, and the friction force will be 0.2 times R2, where 0.2 is the coefficient of friction. One last force that we need to consider to be able to apply the equations of equilibrium is the inertia force, and that will be acting opposite to the acceleration. Acceleration is upwards, so inertia force will be acting in this direction. So now inertia force will be equal to mass into acceleration. Mass of this object is 1000 divided by g, and that needs to be multiplied with acceleration. Now for this body we'll have to take components in x and y direction. That will be simple, which means we will need the angle of the only inclined force with x or y, and this angle is going to be theta, the same that we have over here. So now let's go ahead and take up this free body diagram and try to solve it. First, as usual, we'll be applying sigma y. Let's take up all the forces that are acting in y direction. So we have R2 acting in positive y, then we have the component of 1000 newtons, that is 1000 cos theta, acting in negative direction, hence negative. Remaining all the forces are parallel to x-axis, so they won't have any component in this. Sigma y will be 0 because we are this object is in equilibrium, and that is R2 minus 1000 cos theta. So cos theta value we'll have to find using this particular triangle. Fine. So this is 4, 3. So hypotenuse will come out as 5, and cos theta is adjacent by hypotenuse, so that gives us 3 by 5. So let's take that value over here. So 1000 times 3 by 5. Now that gives us the value of R2 as 600 newtons. Next we will have to apply all the components in x direction. So let's take out all the components in x direction. T1 is acting, T2 is acting in a positive x direction, and remaining all the components will be against this. So minus of T1 minus of Fi minus 0.2 times R2 and minus the component of 1000, that component being 1000 sine of theta. Now let us substitute whatever values we know in this particular equation and start writing it from this position. The sigma x value is going to be 0 because we have considered the inertia force. We can assume it to be any static equilibrium. And on the right side we have T2, which we don't know. T1, we know the formula for this. So let us substitute that in place of T1. And then minus Fi we have found it, that is 1000 A by G. And then minus 0.2 times R2, we found R2 as 600. Let's substitute. Minus 1000 sine of theta. Now sine of theta, we'll have to take it as 4 by 5. Now in this equation, except for T2, all other values are negative. So let's send them to the other side to get the formula for T2. So these two terms, the A terms, let us add them together. We get 1500 E by G. The other side it becomes positive. And of course, the remaining values, let us calculate. So all those values, the remaining all constant values, when we add, we get a value 1020. On this side, of course, it's going to be negative, but when we send it to the other side, it becomes positive. Now this equation, let's call it as equation number 2. Finally, let's take the free body diagram of the last object and again put all the forces acting on this. The weight is acting in downward direction, the value being 250 newtons. P force is to be found. Back side, we have the tension T2 acting. Normal reaction acting here, let's call it as R1. And because the acceleration, the motion is accelerating towards the left, the friction will be trying to stop it, and its value will be equal to 0.2 times R1. Now to bring it into equilibrium, we'll have to apply one more force, that is force of inertia. It will be acting opposite to the acceleration. So on the right side, it's equal to Fi, and its value will be the mass 250 by g mass into the acceleration. Once again, we'll have to apply the equations of equilibrium on this. Let us start with sigma v, all the vertical components. R1 is acting upwards, 250 is acting downwards, total has to be 0. So that gives us the value of R1 as 250. Next, take all the horizontal components. T2 is acting forward, Fi is acting forwards, P is acting on the negative side, and of course the friction force is acting on the right side. This total has also got to be equal to 0. Now we know the equation for T2 from the previous calculations. Let's take it and substitute in place of T2. Plus Fi, we have found that is 250 by g times A, minus P is unknown, and 0.2 times R1. R1 value we have found here itself, that's equal to 250. Let us send P to the other side to get the relation. And yeah, here we get the A terms. When we add up, we get 1750 by G times A, and adding all the remaining constants, we will get that as 970. So this is our equation number 3. Now in all the equations, equation number 1, 2 and 3, we see that acceleration is unknown. So in the given data, if you observe closely, we have been given the initial velocity, final, and time, and the displacement as well. So we will need to find acceleration using this information. So the best formula to use in this case is 2as equals v square minus u square. Except for a, all the other values have been given. So let us substitute and find the value of acceleration. V square is 3 square minus 0 by 2 times 4.5. So we get the acceleration as equal to 3 square divided by 2 into 4.5. We get that value as 1. So acceleration here is 1 meter per second square. Substituting these values, we will be able to find the values of T1, T2 and T3. So here T1, if you substitute this, we get 150.97 newtons. The same if we substitute here for T2, we will get the value of T2 as 1172.91 newtons. And the same if we substitute here in the formula for P, we get 1148.39. So that's the value for P, 1148.39 newtons. Now you may see that we need a lot of time to actually solve this particular problem using this particular method. So there is a very short method available for this if we go for work energy relation, which we'll be taking up in the future class when we are taking up that particular topic. So that's it for this video. Till the next video, see you. Bye.